In this video, we are going to start looking at the different laws of probability. I'll go ahead and say I don't know exactly how many we're going to get through in this video. I'm just going to try to keep an eye on the time and stop before this is too long of one. But let's not waste any time as we go, and let's just go ahead and jump into it. All right, so the first four are going to be very foundational, but also very important. All right, so the first law of probability says that if the probability of an event A is 0, then the event is impossible. Right, and this makes sense, especially if we think back to how we're going to calculate these probabilities, right? Especially if we think about the classical approach to probabilities. Right? With the classical approach, we know that the number of outcomes in event A is what's in our numerator, right? So if out of all of the possible outcomes, all of the outcomes in our sample space, if none of them fit our event, right, meaning that the event can't happen, we would have 0 outcomes in our event. 0 divided by anything, of course, is going to be 0. All right, on a similar vein, if the probability of event A is equal to 1, then the event is guaranteed. Right? So we would see this if, for instance, every event or every outcome in our sample space was, belonged to the event. Then you're just doing however many over the same number. You're going to get 1. It's saying it's guaranteed. Doesn't matter which of those outcomes you land on. You're gonna land in this event. All right, so the third one is puts these two together. All right, so all probabilities must be between 0 and 1 inclusive. All right, so all this is saying is, again, just combining the first and second law of probability. All right, if an event is impossible, right, if the probability of an impossible event is 0, right, then that is the lowest a probability can be, right? Something can't be less likely than impossible, right? If a guaranteed event has a probability of 1, right? Or another way of saying that, if the probability of an event that is guaranteed is 1, right? That means that's the highest a probability can be, right? A probability can't, something can't be more likely to happen than it's guaranteed to happen. That is the cap, all right? Another way that we can write the third law of probability, in my opinion, my preferred way, right, is mathematically, right? So the probability of any event has to be between 0 and 1 inclusive, right? So it can be 0, it can be 1, right? But it can't fall outside of that kind of interval, right? This is one that gets overlooked quite often, especially in later chapters. And so this one can really help you out. If you get this one's just very obvious, all right? So sometimes, especially when we get into chapters 6 and 7, where we're doing slightly more, or really chapter 6, where we're doing more complicated calculations, you mess up a little bit and you can get weird numbers, all right? In this chapter, it's not going to be super common that you're going to mess up and get a number that's negative or greater than 1, but it can happen. And it's good to know when you see that, you say, oh, hey, I must have done something wrong. I need to stop here. I need to go back, check my work, because I can't have a probability that's negative, right? I can't have a probability that's greater than 1, right? So this can help us catch those little mistakes, right? Maybe we just punched something wrong into the calculator. Maybe we forgot to include something, right, when we were trying to get the number of outcomes in our event, right? Whatever it is, just checking on these little laws of probability can help us prevent those types of mistakes. All right, our fourth law is that the sum of the probabilities of all outcomes must equal 1. All right, another way that you're going to see me write it would be as follows. All right, the sum of sum of the probabilities of all of our outcomes must equal 1. All right. Now, a quick word on this. This doesn't mean that the sum of the probabilities of literally all outcomes of everything you could think of, but specifically for a certain experiment. Right? The probability of the outcome of all the outcomes for a particular experiment must add up to 1. Right? So if we're doing kind of a coin flip, right, the probability of heads and tails needs to add up to 1. And it does, right? It doesn't mean that the probability of, getting a heads on a coin flip and the probability that somebody gets into a car accident and the probability that lightning strikes and all of the probabilities should add to 1, but just the ones for a particular experiment. All right. Okay, so those are the first 4 probability laws of probability. We're going to kind of look at some other stuff before we jump back on that law train. If you like to have everything all together, right, stretched out across all of these videos for Chapter 4, you are going to find 10 laws of probability in total. So if you want to have a place in the beginning of your notes or where you've already started this, where they're all together, make sure to leave yourself a lot of room. Otherwise, you might want to, if you're going to put them all together, you might want to save that for the end, just so you know how, kind of, what's that word? I don't remember, but put them all together at the end. That might be easier than trying to guess how much paper you need to leave yourself. But again, let's take a break from that, and we're going to talk about compound events. Actually, I'm not even going to write that up here. We don't really need to. All right, so compound events, these are just events where there's like one or more things happening. That's essentially all we're doing with these compound events. So instead of saying, the probability that we get 1 heads on the 2 flips, we're saying what's the probability that we get 2 heads on a flip and a tails in the second spot, right? Or something along those lines, right? Let's start talking about these. So really there are 2 compound events, and then there's something else that we're going to just kind of stick in there with them. All right, the first one we're going to talk about are unions. All right, unions are the set of all outcomes in event A, event B, or both. All right, so here over to the side, I've got how we notate the union, all right? So the union is notated as A, then this little U, B. All right, so just visually so we know what's happening, all right, we're looking at, all right, the union of these events. All right, let's say that this purple circle is event A, the blue circle is event B. All right, so the union is, and then kind of all around it is the rest of the sample space. All right, so for the union, all right, we are going to count, all right, if we're looking at the union of two events, we're going to look at all of the events in A, right, or the first one in this case, right? We're going to count all of the outcomes in event B, and we're going to count all of the outcomes in both A and B. All right, so that is what a union is. All right, it's just everything in both camps. All right. So when we start looking at calculating these probabilities, we're going to use playing cards a lot. Don't worry if you're not familiar with playing cards, because one, I'm only going to do them in these lectures, and I'm going to try to really explain where everything's coming from. All right. But in that context, what we would be kind of looking at is if we said, what's the probability that you pull a card that is a red card, a 7, or both, right? So we would count any cards that are red, any cards that are 7, and we would count the the red 7 cards, right? Because they're in both, all right? But we're counting everything. All right, now we're not going to be able to calculate a probability for these just yet, and probably not in this video at all, partially due to the fact that they have this overlap, but we'll get to that in a later video. But that is a union. All right, the next one is what we call an intersection. All right, so an intersection is the set of all outcomes in event A and event B. Right, the way we are going to notate that is A with this little N looking thing and a B. All right. So when we get to actually, and you'll see this in just a second, but when we get to actually looking at these probabilities, all right, we'll replace A and B with whatever the events we are looking at are. All right. Assuming that they're short enough that we can really fit them in there. All right. So once again, let's look at this graphically so we can get a visualization of what's going on. Here, all right, again, we've got A, we've got event B, and this definition of what an intersection is sounds kind of familiar, right? It sounds a lot like the definition of a union, right? But it is different because now we're saying it's event A and event B, not A, B, or both, but we're only counting the outcomes that are in event A and event B. All right, so they have to be in both of them at the same time. So for this, we will just look at our little overlap here. All right, that would be our intersection. All right, and with these intersections, we can just do these with the classical approach of probability if that is an acceptable approach, right? An appropriate approach for what we're doing, right? So as long as we can assume all outcomes are equally likely. we can actually do one of those. All right, so let's say that our events, all right, or actually we'll just do this. What is, yeah, that's fine. The probability All right, so we're going to pivot now to the playing card stuff. All right, so let's say we're trying to answer this question. All right, so our experiment as a whole is just we've got a deck of cards. We're just drawing the top card, looking at it, right? So our question is, what is the probability of drawing a red face card? All right, so really we have two events here. All right. Maybe we'll say A is red, B is face. That doesn't necessarily matter, right? Which order you put those in, right? But then we can go ahead and just look at our probability, all right? So in this case, the probability of the intersection. So we're going to have our probability statement here. So P, open the bracket, and then we're just going to put that notation for the intersection, right? In this case, A is red. Then we're going to put our little N looking thing, and then we'll write kind of our B, which is in this case face. All right, so calculating this probability, again, we don't really need to know anything special, right? Because we can just say, well, how many red face cards are there, right? How many cards are both red and a face card, right? So if you don't know anything about cards, right, just kind of running through these, right? So one, probably the easiest one, how many red cards are there, right? Well, it's half the deck. If you don't know, a deck of cards has 52 cards. Half of that is 26. Then you want to think, well, how many of those are face cards? Well, how many face cards are in each suit? There's 3, right? King, queen, and jack, right? For my purposes, I'm only counting cards with faces on them as face cards, so the ace is not in there. All right, so 3, or really probably the better way to do it was this. 3 in each suit, 2 of those suits are red, so we have 6 red face cards. All right, that's the number of outcomes in our event. All right, if we wanted to name them, list them, all right, we probably could because there's only 6, right? But that event would have the King of Diamonds, the Queen of Diamonds, and the Jack of Diamonds, as well as the King of Hearts, Queen of Hearts, and Jack of Hearts, right? That is our event. And then we would just need to divide that by the total number of outcomes in our sample space. As we said, there are 52 cards in a standard deck of playing cards, right? And so we would do 6 divided by 52, which is going to give us a probability of 0.115. Right, and that is how we would find the probability of a intersection. Right, we just need to, again, we need to identify how many outcomes are in our event, divide by the total number in the sample space, or the number of outcomes in the sample space. All right, but with that, we will move on. So this last thing, it's not really a compound event, but it often gets included with the rest of the compound events. But this is what's known as a complement. All right, the complement of an event, right, or specifically we'll say the complement of event A, is the set of all outcomes in S, or the sample space, but not in A. All right, so a complement, the complement of A is just everything but A. So everything else in the sample space except for A, that's what the complement is looking for. All right, so for notation, all right, we can write that out as A, then a superscript C. I'll go ahead and be honest with you, in kind of day-to-day, I don't see this notation that often. Most of the time you're just going to write kind of, if you want everything but, you know, red cards, then you would probably just, there's an easy opposite to that, right? So one, you could just say, what's the probability of no black cards? Or no, that's wrong. If you're looking for red, what's the probability of no red cards? Or you could say, what's the probability of drawing a black card, right? So there are going to be opposites for that. So we're not going to see this type of notation that often. But one thing, a couple other things to note on this. One, I'm just going to add this here. All right, so if you were to add the complement of A and event A together, all right, those should add up to the sample space. All right, so thinking about that example we just did, all right, if you've got red cards and that's your A, then the complement of A would be all of the black cards. If you add all of the red cards and the black cards in a deck together, then you would have a full deck, which represents the sample space. All right, so those should add up to S. All right, visually, this one's a little different. Let's say that this box is the sample space, or actually let's put that outside. So this is the sample space, and we'll say this circle represents A. Then the complement of A, C, right, would just be everything else, right? Everything within the rectangle, the blue rectangle, except for what's in the purple circle. That would be the complement of A. All right, and we will actually end this video with the fifth law of probability. All right, so this is the last one for this video. All right, and this states that the probability of the complement of A is equal to 1 minus the probability of A. Right, and this should make sense, right? The probability of all of our outcomes have to sum to 1, right? If we add up the probability of all of our outcomes, they must equal to 1, right? If you split those outcomes into 2 events, right, then their probabilities must also sum to 1, right? And so that's what we're seeing here. Right, and this one's relatively simple, so we're not even going to run through an example for it. I will say that this is also going to be a very important one later on. I almost guarantee that you're going to forget about it, but I will we'll remind ourselves of this law of probability and how important it is. Right now it's pretty easy to just kind of find the opposite of what you want. So you were not going to use this very much in this basic probability section, but later on we're going to get to some probabilities that are it's either easier to find the probability of A than the probability of AC, so this is just going to be a shortcut. In some cases where it's not going to be possible for us to find the complement of A at all, and so we will have to use this law of probability. All right, but again, I kind of sounded like I was going to stop talking for probably the last 5 minutes, so I will finally stop talking. We'll talk more about that later on, and we will continue looking at these laws of probability in the next video.